Hello and welcome to the video where we will be discussing fatty acids. The specific objectives for this video about fatty acids are listed here. We will be discussing how to draw structures of fatty acids, how to classify fatty acids as saturated, monounsaturated, or polyunsaturated, how to classify fatty acids using omega-N notation, and finally, how to predict and explain trends in melting points among fatty acids. Notice for this semester, we are skipping being able to identify hydrolyzable lipids and non-hydrolyzable lipids. So let's get started with looking at structures of fatty acids. I'm going to have you skip to page 182 in your workbook here. Page 182 shows about a dozen different fatty acids. These are not all the fatty acids that exist. There are dozens of fatty acids. These are the most common that we encounter in the foods we eat and that get used by our bodies. What we'll focus on first is structure. I'd like you to notice this part of the molecule is present in each fatty acid, a zigzag notation that indicates a hydrocarbon chain. I'll call this the hydrocarbon chain, long hydrocarbon chain. Each fatty acid has that component to its structure, and also each fatty acid has this component to its structure, which of course you recognize to be a carboxylic acid. So the name fatty acid stems from those two features. The acid is the carboxylic acid portion of the structure, and the fatty part is the long hydrocarbon chain. So all fatty acids have those two features in common, the hydrocarbon chain and the carboxylic acid functional group at the end. That's what's the same for each structure. Please notice what's different though. You can see that there are, pull this paper out, you can see that there are, among these 12 fatty acids, there are several different categories of fatty acids. This category, and this category. Specific saturated fatty acids, monounsaturated fatty acids, and polyunsaturated fatty acids. You already know what the word saturated means. We discussed that when we learned about alkenes. I'll remind you of that though. Saturated hydrocarbon means there are no carbon-carbon double bonds present in the compound, and unsaturated means that there are one or more carbon-carbon double bonds. So sure enough, this top group of fatty acids, you notice there are no carbon-carbon double bonds. All of these top 5 are examples of saturated fatty acids. There are no carbon-carbon double bonds present. So these are classified as saturated. This middle group of 2 fatty acids are classified as monounsaturated. Monounsaturated means exactly one carbon-carbon double bond is present. Here it is for palmitoleic acid, here it is for oleic acid. Exactly one carbon-carbon double bond in each. And finally, the bottom group, polyunsaturated fatty acid, means that there are 2 or more carbon-carbon double bonds. Linoleic acid has 2 carbon-carbon double bonds. Linolenic acid has 3. Arachidonic acid has 1, 2, 3, 4. EPA, abbreviated EPA, is 1, 2, 3, 4, 5, and DHA, 1, 2, 3, 4, 5, 6. Each of these would be classified as a polyunsaturated fatty acid. It's important that you feel comfortable drawing these structures yourself. You might draw it in the line angle notation as it is here, but you should also feel comfortable drawing it with more of a condensed or skeleton notation. Let's do that together right now for this one. If you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons total. So we could write this structure like this. That's another way to write that same lauric acid. Or we could write it like this. Those are all these three are all the same, 3 different ways of drawing the same structure. That is the same as this, which is the same as this. All 3 of those are different ways of drawing lauric acid. So that's just an example of different types of notation for a molecule. Skeleton notation, condensed notation, line angle notation, and you ought to be comfortable going back and forth among those types of notation. What we've just done, I'm going to go back to our introductory page. What we've just done is practiced drawing structures of fatty acids and classifying fatty acids as saturated, monounsaturated, or polyunsaturated. Let's go back and take a look at those structures so we can learn how to classify fatty acids using this omega notation. You've maybe heard in the news or seen in the grocery store or pharmacy things like omega-3 fats and omega-6 fats. That's what this is referring to. Let's learn a little bit about that. Coming back to this sheet that shows the structures, what you'll notice, a couple things. This little letter right here, that is the Greek lowercase omega. So that's pronounced omega. Omega-7, omega-9, omega-6, omega-3, omega-6, omega-3, omega-3. That's how you pronounce that letter. Notice right off the bat, there's no omega designation for these fatty acids, the top 5 at the top. That's because omega notation refers to applies to unsaturated fatty acids. Omega notation does not apply to saturated fatty acids. The reason for that is the omega notation will be telling us something about the position of the carbon-carbon double bond. So if there is no carbon-carbon double bond, then there is no omega designation. So I'll summarize that here. No carbon-carbon double bond, so there's no omega anything. Omega notation does not apply for these. But for the unsaturated, whether it's monounsaturated or poly, omega notation does apply. And what I often like to say is to recite to yourself the whole term omega-6 fatty acid, for example, or omega-3 fatty acid. And I like to say we never call it omega-3 acid fatty. We call it omega-3 fatty acid. What I mean by that is this is the fatty end of the molecule. These are the fatty ends of the molecule. This is the acid end of the molecule where the carboxylic acid is. So omega-3 or omega-6 notation, fatty acid, means this. Starting from the fatty end of the molecule, start counting the carbons, and when you get to the first double bond, the carbon that starts the first double bond, that will tell you the omega notation. Here's the fatty end of the molecule, not the acid end, but the fatty end. 1, 2, 3, 4, 5, 6, 7. The first place we encounter a carbon-carbon double bond is at carbon 7, so this one is classified as omega-7. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. We first encounter a carbon-carbon double bond here at carbon 9, so this is classified as omega-9. Likewise, this is omega-6, this is omega-3. Here again is omega-6, and so on. So if there is more than one double bond, as there are for these polyunsaturated, it doesn't matter. The omega notation is always referring to the position that the very first carbon-carbon double bond begins. I will say one more thing about this, and that is that you don't see omega-7 or omega-9 supplements. You don't see those sold in stores the way that you do see omega-3 and omega-6 supplements sold in stores. You don't see omega-7 and omega-9 sold in stores. This is because these fatty acids are classified as non-essential. Non-essential, which means your body can make them. Your body can make these. So you don't need to get these in your diet. Your body can make them. These, however, your body needs to either have in the diet or as a supplement. So one more time, omega fatty acid notation refers just to unsaturated fatty acids, and it's identifying the position where the first double bond begins. Let's see what is our last topic for this video. We've just now classified fatty acids using omega notation. The last topic for us to do is look at melting points, trends in melting points among the fatty acids. Before we flip the page back and look at that in detail, I want to say a little bit more about what we mean by that. You already know. You know about fats such as butter, maybe lard, are solid. You know that. And you know that oils such as olive oil, corn oil, are liquid. You know that from your life experience. Olive oil in the kitchen versus butter in the kitchen. You probably know about that. And you also hopefully remember that if something is a solid, it has a higher melting point, which means it must have stronger intermolecular forces. This is what we learned about some time ago. If something is a liquid, that must be because it has a lower melting point. And if it's a lower melting point, that must mean its intermolecular forces are weaker. We have not yet talked about fats and oils. We're specifically talking about fatty acids right now, but just sneak peeking ahead, these are, fats and oils are built from fatty acids. So if you have a fatty acid with a low melting point, it's likely to form an oil. Fatty acids that have higher melting points are more likely to form fats. So this is why we're talking about melting points of fatty acids. It will help us understand why some of the products, fats, are solid versus oils being liquid. So the second video will be talking about fats and oils. Understanding fatty acids right now will help us understand fats and oils in that second video. So again, solid anything will always mean it has a higher melting point, stronger intermolecular forces. Liquid anything means lower relative to solid, lower melting point, weaker intermolecular forces. Let's see why this would be in the specific case of fatty acids. So I'll flip back to our structures page, the structures of the fatty acids. We saw just a moment ago some fatty acids have 0 carbon-carbon double bonds. Some fatty acids have exactly 1 carbon-carbon double bond. And some fatty acids have more than 1 carbon-carbon double bond. So that's one difference among the different fatty acids. The second difference that we've not yet talked about is how many carbons are there. So I'm going to write this down. 2 key differences that you might notice when comparing fatty acids. The two key differences are how many carbons total and how many carbon-carbon double bonds total. Again, the number of carbon-carbon double bonds might be 0, might be 1, or might be more than 1. The number of carbons, we have not counted those or looked at those yet, but let's do that right now. I'm going to zoom out just a little bit so we can see the whole page, like that. If you take a look, we already counted this one. There were 12 carbons. If we look at, let's say, arachidic acid, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This fatty acid has 20 carbons. This one up here had only 12. So the number of carbons can vary from fatty acid from one to another. There is a handy notation. I did not list that as an objective, but we'll do it right now because there's a handy abbreviation listing how many carbons there are so that we don't have to be careful always to count. And that's listed over here. I will call this the abbreviated notation. Like 16, 0, 20, 0, for example. We'll call that abbreviated notation, and what that means is this. The first number tells you how many carbons. This one has 16 carbons. The second number tells you how many carbon-carbon double bonds. This is why all the saturated fatty acids have a 0 for the second number, because they all have 0 double bonds. The monounsaturated fatty acids each have exactly 1 carbon-carbon double bond. The polyunsaturated each has 2 or more, 2, 3, 4, 5, 6. So the first number tells you how many carbons total. The second number tells you how many carbon-carbon double bonds total. And it's those two numbers that can vary from one fatty acid to another. How many carbons total? How many carbon-carbon double bonds total? What does this have to do with anything? Let's think about how it impacts melting point. That's what we're caring about right now is melting point. You already know from having studied intermolecular forces prior this. The more carbons you have, the stronger the intermolecular force. This is the reason for the trend. So this is the reason. The trend itself is this. As the number of carbons goes up, the melting point goes up. I'll say this again. As the number of carbons in a fatty acid goes up, as the number of carbons in anything goes up, the melting point is going up because you have, London dispersion forces will be stronger because you have more overlap between the molecules, more areas for the interaction between molecules. So you would expect that this fatty acid, arachidic acid, 20 carbons, should have a higher melting point than palmitic acid, which has only 16 carbons. So this is the first trend we see. The second trend, which actually ends up making a bigger difference, is looking at how many double bonds there are. And before I summarize it in words, I'd like to show it to you in pictures. Stearic acid is here. It's shown in a different type of notation that we have not seen yet that shows a space filling notation. So each atom is like a sphere. Pretend that you have a model kit in the lab. So here's stearic acid, 18 carbons, 0 double bonds. So this is 0 carbon-carbon double bonds. What we're looking at right now is the effect of the number of carbon-carbon double bonds ultimately on the melting point of that fatty acid. So this has 0 carbon-carbon double bonds. Oleic acid has exactly 1 carbon-carbon double bond, still 18 carbons, so we're not changing the carbons. We're only changing the carbon-carbon double bonds. I see that this has 1 carbon-carbon double bond. Linoleic acid still has 18 carbons, but 2 carbon-carbon double bonds. Linolenic acid, this one here, again, still has 18 carbons, but it has 3 carbon-carbon double bonds. And what I'm hoping you notice as these structures are displayed, the overall shape of the fatty acid that had 0 carbon-carbon double bonds, the overall shape is roughly straight, linear. There is a zigzag in here for sure. This is the zigzag of the bonds between the different carbons, but zag up, zag down, up, down, up, down, up, down, like that. And so overall, it's pretty straight across, linear. But when you add a double bond, you get sort of a kink or bend from the double bond. And then here you have 2 of those bends, 3 of those bends, with the result being that more carbon-carbon double bonds results in a, what would you like to call that, kind of a twisted shape, a less regular shape, a less regular shape like this will mean less overlap or contact between molecules, which will mean weaker intermolecular forces, which will mean a lower melting point. So what I've just done is try to show the reason why. We're about to summarize the what, but the reason why is this. As you add more as a fatty acid has more double bonds compared to a different one, more double bonds will result in kind of a twisted up shape. And the less regular shape like this is a, that's a less regular shape. It's kind of twisted. This is a more regular shape. As you have a less regular shape, the overlap or contact between this molecule and another one just like it is worse. Less overlap or less contact, which will mean weaker intermolecular forces and therefore lower melting point. So that is the reason, but the summary of it is this. The more carbon-carbon double bonds you have, the weaker the intermolecular forces as we just described. And if the intermolecular forces are weaker, then the melting point is lower. So as the number of carbon-carbon double bonds goes up, the melting point will go down. As the number of carbon-carbon double bonds goes up, the melting point will go down. You would expect linoleic acid with 18 carbons and 2 double bonds to have a lower melting point than stearic acid, which has 18 carbons and 0 double bonds. If the fat or oil molecule built from a lot of stearic acid fatty acids, if we build a structure from stearic acid, this would be more likely to give a solid, higher melting solid, as opposed to a lower melting liquid. Again, we're going to see in the next video how it is that these combine to make a fat molecule or oil molecule. Right now we're talking about the trends in fatty acids that will help explain that. So to finish up, we'll return to our introductory sheet to make sure we talked about what we wanted to. We've just explained and so that we can predict trends in melting points among the different types of fatty acids. In the second video, which is next, we will learn how these fatty acids combine to make a larger molecule. Thank you for joining.